And instead of now zeroing out the output value every other cycle, we're going to use validity. So again, in this example, we're now running the calculator every other cycle. So every other cycle we have valid input, we have our valid signal to tell us whether the input is valid or not, and we're just going to use that as a valid condition for the computation that we're performing. So I've included here for reference the syntax relative to the Pythagoras' theorem example. And the change that we're doing, looking at this diagram, is we're essentially just applying valid as a condition on the logic. But we're also going to make sure that the logic is enabled during reset. And this is important because this logic is assigning an output value, and that output value is state in the sense that it's recirculating back as input. We need to reset this circuit, and in order to get into our reset state, we have to make sure the logic is actually valid during reset. So we're generating a valid or reset signal, and we use that as our when condition. And in addition to doing that, it's no longer necessary to explicitly zero out the output. It wasn't necessary before. We could have left it as garbage. It's just a little bit more convenient to look at waveforms with zero values. Now it's going to be even more convenient to look at waveforms that have explicit don't care values. So we can get rid of that, that condition selecting 0 during invalid cycles. So those are the changes. Give it a try yourselves. You can pause the video again and start up when you're ready. Alright, so now we're going to exit out of the slides and jump back to this myth repository. So scrolling down here to the section about getting help when you're stuck with labs. So this becomes important, especially as the labs get more involved. So we put some nice infrastructure in place to help you when you get stuck. So I mentioned before in this repository, if there's anything that we need to communicate where folks are having, where there's an issue with the videos or anything, do check here. And, the labs build on themselves, so make sure if you're stuck on something, you're looking back at the previous labs, make sure you understand the concepts. If you get something wrong in one lab, that might cause you to stumble in the next one. And then third here, we've got these reference solutions. And I hope you appreciate these. We spent a lot of time getting this in place. My birthday's even, so I'm going to open up this one. So what's coming up now is a reference solution inside a maker chip. You'll notice in the source code that you can't see the actual code for the solution. The TL Verilog code is included here through this include statement. But we've made sure that the code itself is not visible. So even in the navTLB, which normally would be visible, we've made sure that it's hidden in the reference solution. You do, however, have access to the diagram. I need to enter some legal parameters here. So we want to view the calculator solution for this lab that we're on, which is slide number 42, and we can get that by entering 42 in here. When we get to the RISC-V labs, you'll need to comment this line out, and then you'll get the RISC-V solutions, and again corresponding line number for the RISC-V labs. But at this point, I want to see the solution for the calculator on line 42. This might not actually correspond exactly. We'll make sure the slide numbers match up by the time you're doing the labs. But what I was saying is, to understand a lab, if you're confused on something, you've got the diagram accessible. If you're not sure, say what the syntax is for a divide, so you're not sure how to do the quotient expression, you can hover over it and see the expression syntax. And it's useful for if you're confused about how the pipelining works, where your flip-flops are supposed to be, how your logic implies flip-flops. You can use the reference solutions to understand what it is we're trying to ask you to code up. And of course, you've got the waveform as a reference as well. So, maybe you don't understand the 2-cycle cadence. You can consult the waveform to understand the behavior that you should be implementing. And what's new here, which is only available in the Myth1 and Myth2 MakerChip URLs, is this Viz tab. So this is a feature that's coming in MakerChip. It's not ready for production yet. It's not ready for deployment. But we've used it to put together some assistance doing the labs. So you're seeing here a calculator representing what's happening in the calculator reference solution. And you can step your calculator in time, and we can see the first operation coming through, this being the value in the calculator at the time. So 0 times the value coming in, val2, which is 1. 0 times 1 is 0. Here we're getting another 0 times 1, not much interesting happening by random chance. And then 0 times 5 results in 5. 0 plus 5 results in 5. And then that 5 comes up here as the value in our calculator for the next computation. And this computation happens to actually be an illegal input, so we're not corresponding to any operation here. Our reference solution is resulting in 0 for that. And again, no operation here. 0 plus 3 is 3, so just kind of stepping through. 3 times 15, 45, and so on. One important thing to note, you will see negative numbers, and you may have stumbled over this already. I apologize if you have. There's no, I haven't suggested any protection for underflow. This is not a valid cycle, but we might by random chance come across some other negatives. I guess we didn't, but oh, here we go. So 0 minus 12 is minus 12, and the next cycle, so in the visualization we're interpreting that minus 12 as a signed number, but our calculator is not treating that as a signed number, so the unsigned number is underflowing, and we're getting this ridiculously large number. So we haven't built in any protection for that. We haven't built in any interpretation of our numbers as signed numbers, so just keep that in mind. Okay, so that's the reference solution for calculator. In addition to the reference solutions, going back here and scrolling up, we've also got starting point shell code for you that includes the visualization, and for the RISC-V labs, some additional stuff. But if I open the one for the starting point code for the calculator labs, which I didn't suggest that you start with for the earlier ones, but if you want to open up this now for your next calculator lab, you'll have the visualization available. And this should automatically, maybe you have to enable the visualization by uncommenting this, but you can put your calculator code here, make sure it's lined up properly in the pipeline so your stages are lined up appropriately, and you'll get the visualization. Okay, so I guess you have to uncomment this, and this may or may not be changed when you actually get to the lab yourself. But that gives us the visualization. I have no functionality here, so my calculator shouldn't be doing anything at this point. And I can see that nothing is happening. That little pop-up there, I should have left that. As I said, the visualization feature is not ready for deployment. It shouldn't cause any trouble, but you might see some sort of anomalistic behavior with it. So anyway, no actual logic here, so we don't see anything happening. But as you put your functionality in here, you'll start to see that the calculator start to function. Also, jumping back to this one again, the mem and recall buttons here, this is for the next lab that you're going to do. So in the next lab, as I will explain shortly, you'll be adding capability up here with the memory to remember values that you've computed from the output, and then to recall values from the memory into your calculator. So here we're doing a recall. We should see this 0 value end up in the value in the calculator for the next operation. All right, so now you can go into that next lab where you're implementing the mem and recall, and you can do that within this shell if you want to have access to the visualization. And we'll make use of the visualization as we go forward with the RISC-V labs. It should be a lot of fun.